the capacitors. And what we can say at this stage is that whenever we consider this system, it is useful to make a connection with the energy which can be stored in these systems. And the energy that can be stored in these systems, it can be described using the energy density. So the energy, it can have units of joule, and the energy density, it can be described, of course, as joule per meter cubed, and this is equal to the permittivity times electric field squared. Okay, so this is how we can describe the energy density whenever there is some electric field, and this one, it is relatively easy to conclude because the work done whenever we try to construct a system, can be described like this. So here, this is, in fact, this is equivalent to 1/2 times the potential times dq. Okay, let's not forget that we had before a while the summation between the potential VI times QI. Now, the same way that we use the summation to find the energy that was stored in the system, which had the point charges, we can also use it this way. Okay? When I say this way, we can represent it as such. And here, this dq, this is equal to the charge density times d volume. Now, this is the potential. I don't want to write the volume as V because it can be misunderstood for potential. But this is meter cubed, okay, and this is coulomb. Okay, so this is the volume, this is the charge density. So they make up for the charge here. Okay, and now we know from the postulates that or we can write this one. We know that the charge density, this is equal to the divergence of the vector field D. Okay. If you remember, we had two postulates for electrostatics. The first postulate for electrostatics, it was that the divergence of E, it was equal to rho divided by epsilon 0, and the curl of E, it was equal to 0. So if we multiply both sides with epsilon, we get the divergence of the D is equal to the charge density. So at this point, we can write again, this is equal to the integral of the divergence of the D field times the potential times V integrating over the volume. Now these all expressions are equal, so this is also equal to this. These two terms. And if we do a couple of manipulations, here we can wait a second, this is D. If we use a couple of manipulations, we can find that the work is equal to D dot product with E, integrating over some volume. Okay. Now, it looks like the charge density, we can write this one for electrostatic field. This is the D dot product with E. We can extract the permittivity out. We can write this one permittivity times E dot E. And this is also equal permittivity times E squared, because we know that the dot product of a vector with itself is equal to the magnitude squared. Now, given this charge density, we can also use this expression to find the capacitance for specific geometries. For example, we can assume a parallel plate capacitor for a parallel plate capacitor. We can find that the energy stored in this parallel plate capacitor, it can be expressed as 1/2 times the energy density, which in this case we can write this one as integrating the permittivity times E squared. In a parallel plate capacitor, electric field is always V divided by D. Okay? The potential difference between the plates, where this is the capacitor, this would be the delta voltage, this is the C, and this is the electric field here. We have this expression, this is V over D all squared. So this is the energy density integrating over the volume. Now these quantities, they are all constants. We can take them out of the integral, and here we get 1 over 2 times permittivity V squared over D squared times the volume, and the volume, it is equal to the area of the capacitor times the distance between the two plates, okay? And we can notice that we can cancel these D's, and we get here 1 over 2 permittivity A divided by D times V squared. We remember that this was equal to the capacitance, so this is equal to 1 over 2 C V squared. Okay. And so this is, we know from the previous course in physics, you might remember that 1 over 2 CV squared, it was equal to the energy of a capacitor, or 1 over 2 Q squared over C. Okay. These two expressions, they are all equivalent to each other. Now, we can use this energy to also determine what is the expression of the capacitance for complex systems. So let's consider a coaxial cable capacitor, which is, we have an inner so here we have a capacitor in the form of a cylinder that we did in the previous session, and we want to find what is C. Find the capacitance, and in order to find this, what we can do is that we can first determine what is the energy in this system, and the energy, it is going to be written again as this is equal to 1 over 2 times the permittivity times E squared integrating over the volume. Okay, and if you look at the notes of the previous session, we can substitute instead of the electric field the expression which was somewhat related to Q over 2 pi epsilon 0 RL. Was there anything else? I believe this was all. Can you check this? Is this true? So here we have 1 over 2. Permittivity is a constant, we can take it out. And then the electric field square, we get, in fact, it's this expression square. So it's going to be Q squared over 2 by, is the permittivity in there? It is, permittivity of RL. This is all squared, integrating over the volume. Now, how can we integrate over the volume of a cylindrical shaped object? So now, what we can think here, we can assume that we have the volume of a piece of paper. So this is a cylindrical shape, and we increase the volume of this one using an infinitesimally small volume, which is the volume of this piece of paper, and we wrap this around this. If we wrap this around this, we can say that the volume of this one is this side multiplied by this side times the thickness. The thickness is going to be equal to dr. So d volume, we can write this one here, the infinitesimally small volume, which can be used to integrate and to get the volume of the whole cylinder, it can be written as the outer, so what is the area here of this outer object? Let's consider this one for a moment. The area, it is equal to 2 pi r, okay, whatever the radius is. This is 2 pi r times L. So 2 pi r is this side, which is going to make the circle. So this is 2 pi r, this is L. times dr. So we substitute these terms here. Let's keep it d-volume for a moment. And this will be equal to, we can take out of the integral all the constants, and we keep inside whatever terms which are not constant. So here we get permittivity times q squared in the volume. This is a constant, this is a constant, so we get 2 pi L, and then inside, what is left is that we have here 1 over r squared. Okay, this is 1 over r squared. There's this r and this r. So we have r dr. And then on this side, we have the 2, it was always here, divided by 4 pi squared, this is multiplied 4 pi squared, permittivity squared, L squared, okay? So then we can cancel out a few terms. This is 1 over r dr integrating from a to b. This is going to be equal to the natural logarithm b divided by a. So overall, this expression, this is equal to q squared divided by 4 pi permittivity L ln b over a. So this is the energy in the system, and what we can do here is that this energy here, we simply equal it with this term, okay? So we compare these two, and we can notice that here we can cancel out the q squared, we can cancel out the 2, and just by looking, so what we did here, we calculated the energy which is in this system. We compare with this, and we can also notice that this capacitance, it is written here. So again, we can conclude that C is equal to 2 pi permittivity times L divided by a geometric parameter, which is the ratio between the outer diameter and the outer radius to the inner radius, taking also the logarithm. So this is essential to understand the energy consideration in the capacitors and overall. The next topic that we are going to discuss is the boundary conditions. And the boundary conditions, this is defined as given as such. So far, boundary condition, but we also, it's worth mentioning that these boundary conditions, we have to see them, how they look like in Cartesian coordinates, in cylindrical coordinate system, and spherical coordinate system. And now, so far, what we have done is that we have given a Q, let's say Q or charge density rho, and the question was find V, which as a function of R, or find the electric field as a function of R. So this was the type of problems that we have considered so far. Now, with boundary condition problems, what we will give is the following. Given potential V1 and given also potential V2, find how the potential changes in these coordinates. So the question now is find V as a function of X. So this is, or similarly, we can assume that we have a plate which is charged. We have another plate which is charged like this, okay? We may ground this plate at topsoil, and then this plate we can keep this at a potential V1, which means that V2, it is 0. So we will give these expressions, and the question will be, how does the potential looks like as a function of r, theta, and phi? So we will have to find, sorry, this is the question mark. So this is a new type of problems that we have to consider. In order to do this, we always, or not to do this, but in order to find these potentials, so it looks like kjo është një panjohur, ky potenciali këtu është e panjohur. Për të gjetur panjohura, ne duhet të shkruajmë një ekuacion. Të cilat ekuacione do të jetë ky funksioni jonë. So, what type of equation do we need? We are going to see that the equation that we are going to obtain to solve these types of problems is going to be a differential equation. And differential equations, they describe how the potential changes as a function of the space parameters, okay? And this is described by the Laplacian, or a term, which is here, the dot product between two del operators. Or, let me write it here, so we're going to see that this is the Laplacian, and this is equal to the dot product between two terms. You can check at the back side of the textbook, or you can use any formula cheat sheet or formula sheet to find what is the Laplacian in all these three coordinate systems, because it certainly looks different. Now, we start the same discussion. We always, whenever we want to derive something, we just write the postulate of electrostatics, which is that the curl of D is equal to the charge density, and sorry, this is divergence of D is equal to the charge density, and the curl of E, it is equal to 0. So, given this, we can, if this is true, so these are two postulates, right? Then, if this is true, then we can say that E is equal to minus the gradient of some potential. So we know this, and then we can, what we can do is that in this expression here, we can say that the gradient of permittivity times E, so this is D, right? So this is a D. This is equal to rho. Then we can take out the permittivity. So this is the second step. Then we can take the permittivity out, and we have the divergence of E is equal to rho. Then we substitute this expression here, permittivity times dot product of minus the gradient of V. This is rho, so we have not done much difference here. This negative sign, we can take it out, and so we can take minus the permittivity. We have here this divergence, this V. This is equal to rho. Then we can couple these two, okay, and then we can write that and coupling these two is a dot product between the two del operators. We get a Laplacian. The Laplacian operator over V, this is equal to minus rho divided by epsilon 0. So we obtained this equation, which is called the Poisson equation. Which describes how the potential changes given the original charges. Okay, the solution of this is going to tell us how potential is changing in case the charge density is equal to 0. So in case we have this, then we can obtain the Laplace equation. So the Laplace equation, it's a simplification of the, not simplification, it just corresponds whenever the charge density is equal to 0. And then we just need, probably we don't need to write all of them on the board, but because you can check the cheat sheets, but as a small reminder, the Laplacian operator in Cartesian coordinate system, it looks something like this. The second derivative with respect to x. We can put here the V plus the second derivative with respect to y of the potential plus the second derivative of the potential with respect to z. This is equal to minus rho divided by epsilon 0. So this is Poisson equation in Cartesian coordinate system. So what we need to do is we just take the dot product between the dead operators. The dead operators you can get them from as we said from the textbook. I'm not going to write the Poisson equation in cylindrical coordinate system, but let me write for you the spherical one. So it's going to be an expression 1 over r squared derivative with respect to r of r squared dv over dr plus 1 over r squared sine theta, the derivative with respect to theta, v over d theta of sine theta, derivative of v with respect to theta. This is so we find the space derivative with respect to r, the space derivative with respect to theta, and we have also the third orthogonal coordinate system, which is the angle phi. And for the angle phi, we add here plus 1 over r squared sine theta, 1 over r squared sine theta squared, derivative of the potential with respect to angle phi. This is equal to, minus rho over epsilon 0. So this would be the Poisson equation for the spherical coordinate system. And we can see an example where we can be given a potential V, which is a function of x and y, and this one can be written as a constant A, e to the power minus kx sine ky. Now, the question can be the following: does this potential satisfy Laplace equation? So, does this potential satisfy the Laplacian equation? So, what is the Laplace equation in Cartesian coordinate system? It is this equation, but with rho equal to 0. So, actually, let's write here Laplace equation is this expression. The second derivative, the Laplacian operator of the potential is equal to 0. So, for this, let's find what is the derivative of v with respect to x. The derivative of v with respect to x, we see that the x fits here. So this is going to be equal to minus k times e to the power minus kx sine ky. The second derivative of v with respect to x again, we will bring a second minus k term, which comes from the derivative of this function. So we get minus k times minus k, a to the power minus akx sine ky, and here we get k squared a e to the power minus kx sine ky. Okay, we got this. Then we have to find the derivative of potential with respect to y. Y, it appears only in this other term here, and we know that whenever we take the derivative of sine ky, we are going to get cosine ky, but with a k at the front. Okay, so the first derivative is equal to k times a to the power e minus kx cosine ky. Okay, and let's not miss this. And the second derivative of the potential with respect to y, this would be k times k. Now the derivative of cosine, it is equal to minus sine, so it is worth now k times k, it's equal to k squared. Allow me to write this one right away. So this is equal to k squared, and the cosine, the derivative brings a negative sign in front, so this is minus k squared a e to the power minus kx sine ky. Okay. So now to check for the Laplace operator, we have Laplacian. We have also derivative of potential with respect to z, to the third orthogonal coordinate system, because we have also this, right? What is dv over dz? We don't see the z in this expression at all, So we get the following. We don't need to detail this too much. But now we have all the terms which will be substituted into this Laplacian operator. And then what we can observe is that if we add this term here and this term here, we get what? And also a problem with this, we get 0. Because the second derivative of the potential with respect to x squared plus the second derivative with respect to y squared plus the second derivative of the potential with respect to z squared. The question is this equal to 0? So we are checking for this. And then we notice that if we add all of these, we are going to get equal to 0 because we get k squared times ia minus kx sine ky minus a minus kx sine ky, and this is equal to 0. So it looks like this specific potential satisfies the Laplacian equation. Now this was the an example. Let's see. Now let's have a look at the let's assume that we have two conducting plates that are held at an angle alpha, and one of the plates, it is grounded, the bottom metallic plate, and the top one is the potential V0. Okay, and we need to find what is the potential. So here, what is the potential at any point here? So again, this classifies as a problem of boundary value problems, where we are given two boundaries. We need to determine how the potential is changing at every angle. Now, at this part, we have a solution. The solution is the following: the Laplacian of this potential is equal to minus rho divided by epsilon 0. Since we don't have a charge density which is provided, this is simply equal to 0. So we have to solve for this. Okay. Now, since we have this problem, we have first to identify what is the symmetry of the problem. So, are we going to use Cartesian? Are we going to use cylindrical or spherical? So let's not forget this is a plate which extends like this. It has a surface area at the top, and this is the second plate which extends like this. And here we can also argue that the coordinate system which is relevant to consider is r, theta, and z. And r, it is defined as because we should remember that this is r, okay, this is theta, and z is extending so this is the z, okay? Theta is the angle that we use. Now, what we can say here, or we have to look for the symmetry of the problem, and it looks like along this plate, here r is equal to 0. Okay, here r is larger than 0, it has some value, and also here. And the possible question is this: how does the potential change from this point, where it is 0, to this point? Does it change? Well, it does not change from which we can conclude that the derivative, so the derivative of the potential with respect to R is simply equal to 0. Okay. So we observe this fact. Another factor which we can analyze is that since the bottom plate it is all grounded, that means that this is 0 volt, this is 0 volt, this is 0, 0, and so on. So moving across this line or changing Z is not going to change the potential, which means that the derivative of the potential with respect to Z is also equal to 0. So we know that when we construct the Laplacian, we will have for sure derivative with respect to R, derivative with respect to Z, and we're going to have also the potential, the derivative with respect to the angle θ. Now, this is different from 0 because we observe that as we're changing the angle along this path, the potential is changing because it's converging from 0 to some V0 at the top. This is cylindrical coordinate system. In the previous session, we wrote the Laplacian operators for Cartesian and the spherical coordinate system. Now we have a chance to write it down for the cylindrical one. And this Laplacian is equal to 1 over R, the derivative with respect to R, of R dV over R, plus 1 over R squared times the second derivative of the potential with respect to the angle phi, plus the second derivative of the potential with respect to Z squared. This is all equal to 0. Now, when we look at these terms, we said that this is 0, and Z, this is also 0. That means that this whole term is gone, and this is also gone. Now, so what we can do is that we are left only this term is equal to this 0. At this stage, we can multiply both sides of the equation with R squared, and we simply get that the second derivative of the potential with respect to phi, this is equal to 0. So in order to solve this differential equation, we can integrate twice. Okay. So the second derivative is 0. That means the first derivative is a constant value. So we get dv over d phi is a constant c1. Okay. Because if we come backwards by taking the derivative this way, we know that the second derivative would be equal to 0 because this was a constant. Okay. And then we integrate again. So with green color, we're showing integration into Europe. And the potential, this will be equal to C1 times angle phi plus C2. That's fine. We solved the problem. That's it. Okay. We also know that. So this is how difficult this problem was. So you have this, we get this expression. But now we may have to apply the boundary conditions. The boundary conditions, they state that the potential when the angle phi is equal to 0, this is equal to what? So when the angle is 0, what is the potential? It is grounded, so this is 0. The second boundary condition, it states that when angle phi is equal to alpha, this was equal to V0. So let's not forget, these were the two boundary conditions. And then we apply them one by one. We see that the potential is equal to C1 times the angle phi, which is 0, times 0, plus C2, this is 0. Okay. So from the first equation here, we see that the second constant C2, this is going to be 0. Okay, so this is gone, this is 0. Then, when we apply the boundary condition at angle alpha, we find that V is equal to C1 times alpha. The angle is alpha, we are substituting it here. This is equal plus 0, because C2 is 0, we found it. This is equal to V0. So we had two constants, okay? So since we have two constants, C1 and C2, we needed two boundary conditions to determine what they were, okay? And we found it looks like C2, it was 0, and C1, it is equal to V0 divided by alpha. V0 divided by alpha. And then the potential is V0 divided by alpha times the angle phi. So this is the potential for this geometry, given the initial conditions that we had. Okay, do you have any question for what we did so far? Any question? We have another 7 minutes, a short amount of time. Okay, now this can be all for today. We will continue tomorrow because we may not have much time to solve another example because there are very few minutes left. But if you have any questions, please list them.